Give it maybe another 30 seconds and then we'll get started.
Sounds good.
Okay, Jared, you want to go ahead and get started? So this is Jared Wolf from Circuit Dojo.
Cool. Thanks for joining my presentation on securing MCUBoot in 5 minutes or less. I'm honored to be here. Thanks to everybody on the Zephyr Linux Foundation team here to put on an awesome event. I've already seen a couple of presentations. It's awesome. Though this title, this presentation is titled "Securing MCUBoot in 5 minutes or less." I've kind of expanded it out a little bit longer, and there'll be plenty of time for questions at the end. So kind of a mixed match of everything. So let's get started. So first, a little background of who I am. Hey, I'm Jared, also known as Circuit Dojo. I am the sole developer of the NRF 9160 Feather, among other things. Previously, I spent a lot of time in Silicon Valley developing hardware for small and large companies. Now I focus on helping clients make their products reality. So I'm doing that full time here in Connecticut. Along with my consulting, I stumbled onto a happy accident that's been keeping me quite busy, and that is the NRF 9160 Feather, as I just mentioned. It's designed from the ground up with the use cases that were most interesting to me at the time. Some crazy low power functionality, UFL connectors for GPS and LTE, onboard storage, and more. The picture you actually see here is one that I hand assembled, which is kind of crazy. If you look at the pitch on that module, they're very small. This is a 4-layer board and it's a OSH Park board. All the other parts are I bought them from DigiKey. So, but this talk isn't specifically about hardware. It's about getting the hardware working over long term, making sure that it's very stable, so maybe sprinkling some improvements in there over time, and
Sure.
maybe some. Go ahead.
Sorry to interrupt, but I think the slides aren't updating for anybody. So
okay.
I'm still just seeing the main slide page.
Let me see.
Now that shows us the board. So whatever you did there.
I must have selected the wrong thing here. I put it in, dang it. Is it going full screen now or no?
No, I still just see kind of
all right.
Usually when it stops updating, it's sufficient to just unshare and reshare, though. Even if it's not full screen, it should be okay.
Yeah, I'm using Keynote, so it's whenever I put it into full screen, I don't have the ability to go back to Microsoft Teams and select the screen. So I guess we'll just have to play by ear here.
Yeah, that what we're doing right now. So
yeah, let me. One sec here. That's a bummer. So let's see, what was I saying? So this guy, of course, runs on Zephyr. So that's one thing. This is like kind of what brought me to be here in the first place. So let me see if I can get my notes. Grab my notes. So it's not specifically about hardware, but we're talking we can fix bugs, and we're going to do it securely. So what we're going to do is we're going to enable device updates. While updates are not a new concept, Zephyr has made it easy for you to enable the bootloader and update your device over various channels. We're talking about over the wire, over the air, Bluetooth, everything. It's critical and extremely important piece of your connected device, obviously, when we have to fix, when there's fixes and new features, and it's critical to your infrastructure. So I'm going to be going over some of my learnings with the NRF9160 Feather, not only enabling OTA updates, but making sure that they're secure. So what's exactly comes with Zephyr, and what can you do to get started right now? By default, Zephyr ships with a default certificate for signing update packages. While this is useful for debugging and testing, it's definitely not recommended for production use. The main reason being is that anybody could push an update to your device and overwrite your device's firmware. It's an important security mechanism to reject updates that are not signed by you. As mentioned before, there are a ton of smart people, some of which are here in this room, virtual room at least, who have fully integrated MCUBoot into Zephyr, in most cases adding MCUBoot as simple as adding a configuration variable. More on that in a second. For managing devices locally, MCUBoot uses MCU Manager, a CLI tool for device updates over wire. As many of you know, that's kind of like the de facto tool for that. But you can also use it not only for sending an update package, but you can also query and send remote commands to your device as well. Finally, Nordic has added some great functionality for the NRF9160 through their NRF Connect SDK, which includes FOTA or firmware over-the-air download module. Makes it super easy to download firmware via an HTTPS endpoint to an NRF9160. I've already leveraged that a ton using the NRF9160 Feather from all my projects that require firmware over-the-air updates or capabilities. So let's get enabling updates on our device. So there are some prerequisites that ensure that your device will work properly. In most cases, devices that already have this defined, you don't really have to do anything. So in my upcoming presentation on hardware and Zephyr, I talk a little bit much more about device tree definitions. But for a fresh device, you might have to jump into devices configuration, device tree definition. So we'll go over that right now, and then if you want kind of like a more in-depth or kind of more better introduction, you can check out my talk tomorrow. So we're going to go. So if you're using a custom device that you've created, you're probably going to have to go into and create kind of your own MCUBoot configuration. These files are located in bootloader, MCUBoot Zephyr board, so it's kind of a long directory structure. But once you're in there, you can probably notice that there are a bunch of other boards in there, including the NRF9160 Feather. In this case, I've configured this guy to work over serial UART. There is no USB PHY on the NRF9160, so UART is the next best thing. There is some extra functionality here, like a boot up delay and indication LED. It makes the user experience a little bit better. Some of those things actually contributed to the MCUBoot repository because it just kind of makes sense. So you want an LED to turn on when you're in MCUBoot. But you may be asking at this point, where do we find the device, like how it's partitioned? On other device platforms, that information is usually in like an LD file or a linker script. So let's see where this partition information is stored in Zephyr. It's in the tree. So partitions are defined in your .dts files, often in the /0 node. The definition for the NRF9160 Feather is a bit long, so I'm only kind of showing you guys like a little snippet of the Flash definition, but it should look familiar for anybody who's played with the device tree, and also should look familiar for anybody who's kind of played with the linker script. You have your like starting addresses and your ending addresses, kind of like in this case you have some partition names. In most cases, for any type of over-the-air update infrastructure, you have usually you want to have enough room to split at least into 2 partitions. It's not any different here with Zephyr. That way you can update a device without corrupting the previous partition. And that's also very true for if someone tries to update your device with some other key, it's not signed properly. You don't want that unsigned binary to like wreck your device. So it's extremely important, and especially for devices that like the NRF9160 Feather, they're deployed in remote places and they may not have sufficient cellular signal. So the cellular signal could drop in the middle of an update. You could get a corrupt packet or anything like that. So it adds that extra bit of robustness to your device. Cortex M33 devices like the NRF9160 do require some extra work because of the trust zone functionality in the ARM chip. The bootloader is compiled as a secure partition, while the kind of application side is compiled as a non-secure. I'm not really going to go into too many of those details, but that does kind of change things up, and Nordic is doing a lot of stuff on their end to kind of bundle everything together properly and size partitions correctly. They're actually kind of doing it dynamically, which is interesting. But you can check out the Circuit Dojo NRF9160 Feather kind of device tree definitions, or even their development kits and stuff. You can always take a look and see how that's done, especially if you're trying to bring up your own device. So at this point, let's say you're already working with a device that's defined in Zephyr's, in the boards directory in Zephyr. All you have to do at this point is actually enable MCUBoot. So that's the one configuration variable that you need to do is config bootloader MCUBoot. This will enable building and merging of the bootloader to your output hex.bin or .bin. In this case, 99% of the time, it's going to be merge.hex. And now what we'll do at this point is I'm going to merge with the kind of the title of this talk is we can start our timer now to actually enable secure updates. So we set the config bootloader MCUBoot variable, and that only enables MCUBoot. This doesn't really secure application. Going back to what I said before, using the default certs, not secure. So what we're going to do is generate certs for signing and your application update images. So let's generate that certificate, and the first thing you want to do is change there's a tool in the MCUBoot root directory. It's called image-tool.py or Python script, and we're going to use that to generate an RSA key. When you do this, so in this case, the key that's going to be generated here, it's called your key RSA 2048.pem. So this is the key that will get kind of spit out of that script, and generally you just want to keep it in that directory because that's where all the other default certs are. You can put them wherever you want, but in this case, you might have to do a little more tweaking to get Zephyr to find it. You also notice that, like I mentioned, this folder has all the default keys for Zephyr, so you might as well just keep it together. Now, you've created your cert. Now you have to actually tell your application, or you have to tell the Zephyr where to find it. So you can either create a separate .conf file, or you can put it in your prj.conf, depends on what you want to do. In this case, I'm using an external mcuboot.conf. This is also kind of the way, I believe it's in the Zephyr documentation, where you're kind of creating a separate file to define what signing key you want to use. Make sure that you set the name of config boot signature key file to whatever the name of your signing key is. So in this case, I'm just keeping it consistent with the one that I generated. So your key RSA 2048, and it'll look in that directory in MCUBoot and find it there. Finally, because we're using another config file, we're just going to have to add that to our cmake list.txt. So it's telling Zephyr, hey, we have this mcuboot.conf, and we want to add that to the list of files, so we can find anything else that's in there. So it'll find those two defined variables they type RSA key file, and it'll be able to take it from there. And then finally, we're going to build our project and make sure that you use the -p, just a kind of clean build, start from the beginning, make sure that there's no weird warnings or problems. Usually when you're building a Zephyr project with the default key, you actually get like a warning being like, hey, you're using the default signing key. We do not recommend this. So that should not show up. So make sure that that's the case when you are building your project. So once your project builds, Zephyr will give you an app update bin within your build Zephyr folder. That's pretty standard for any project that has MCUBoot enabled. So that app_update binary file is the file that you use for firmware over-the-air updates. So if you're delivering it from HTTP or doing MQTT or anything like that, or Bluetooth, that's the file that you're going to be using. It's also the file that you're going to be using with MCU Manager. So that's the one that you're going to grab. If you want somebody to, update with MCU Manager, that's the guy that you want to use. Here's some examples of how I'm doing it with the NRF9160 Feather. Should look fairly familiar to many of you. So I'm using a custom version of New Manager, which is basically MCU Manager. And right here, I'm uploading it over Serial, and I just took kind of a screenshot of just sending the raw data to the device itself over USB to UART. And then also, here's the command line utility for kind of the cloud cloud infrastructure I've been kind of building on the side, and that's just sending that binary up to the cloud and actually pushing it over MQTT. It gets the download link, and then the device will use Nordic's FOTA download capabilities to actually download it to the device. And so that's pretty much it for, there you go. That's hit the timer. We're done. That's how you can secure your device for firmware over the air for MCUBoot on Zephyr. I know there's us. We got a few minutes left here. Feel free to ask questions. Here's a resource.
So there's a question, Jared, from the chat that was, do you know if it's possible to replace the keys in case a key was compromised?
So that's a good question. So that's tricky. You'll probably have to reflash the device, unfortunately, which is not the answer you probably want. Because the only way to you would have to reflash the bootloader with a different key if it was compromised. So generally, that's why you have to treat your signing key with. You need to make sure you're not committing it to repositories. You're not sharing it on a public S3 bucket or anything like that. That stays on the machine that's going to be signing the images that you're going to be using in production. You do not want to get that thing out, especially if its security is on your mind.
Okay, so let's see. There are a couple more questions. Let's see if we're on. Let me get back here. Is it possible to encrypt the application payload using something like AES-128 and make the bootloader hand the key to the application decrypt that would in turn decrypt it before executing?
So this person is asking, basically, how can I encrypt the bootloader payload even more? I've actually not played with that in Zephyr. I don't know if there's a way to do that out of the box. You might have to, on the kind of bootloader side, you might have to create your own bootloader to handle that decryption process. And if that's something important, that seems to be a little bit out of my scope of where I'm focusing. So yeah, it would probably likely require a custom bootloader to get that done. So I don't think Zephyr has that ability. But if somebody knows, please correct me if I'm wrong.
Okay. Then there's a question about, does MCUBoot support chained certificates?
Ooh.
There's another issue for implementing that.
So David's one of the maintainers for MCUBoot, and it's something.
Yeah, David. Yeah.
I think you were saying, David, that that's a work in progress. That someone submitted a PR for that.
Yeah, it's not quite ready for as a PR. I'll post the issue link for it.
Okay.
Thanks, David.
Let's see. How long does it usually take to perform a serial DFU on a typical 9160 app?
So when I'm doing it over this guy, it can be done, and I've actually changed Newt Manager, modified MCU Manager to transfer at faster speeds. Because before, I think the limit is like 115.2. I'm doing it all over one meg baud, which is a little bit faster. So it's like 12-ish seconds, depending on how big your application size is. And unfortunately, that's as fast as the NRF 9160 goes. So it's comparable to flashing with like a Sager or anything like that. It's a little bit slower, but it's definitely usable. I have customers all over the place using just using the bootloader only, and if they have to send an update to a customer, they just pop it on, and it's pretty straightforward.
Okay, and just to clarify, that you're getting around 12 seconds when you're doing the 1 meg baud rate.
Correct. If it was like the 115.2, it's like 45 seconds.
Okay. Let's see. Can I replace the bootloader via the bootloader, or do I need to use like JTAG to replace the bootloader?
I believe, and maybe David could speak to this more, but I believe there's a way to update the bootloader that I don't know how well that's integrated with Zephyr in terms of like how if you can send a separate image. But generally, the way I always do it is through over the wire over JTAG SWD.
Generally, the bootloader is assumed to not be updatable from a security analysis point of view in a final device.
I think that might be a Nordic specific thing. I think Nordic made some changes so you can update the bootloader from them, but generally you can't with MCUBoot out of the box. But I think Nordic changed some things there, so you can update it on bootloader.
That's mostly just because MCUBoot's like a second stage bootloader, and there's another bootloader that can do the updates. You always have a first stage that you're not going to be able to update, whether that's MCUBoot, a different instance of MCUBoot, or an SOC specific updater or bootloader. You still need something that can't be updated for security.
Okay. Is it possible to hook a secure element within MCUBoot to offload the signature verification and storing of the public key?
Yes. There's 1 or 2 instances of that in the code already. It's not trivial, but it is present.
Okay. I think I got all the questions. Let me know, someone, if I missed anything. Okay, anyone got anything last minute? Otherwise, thank you, Jared.
Yeah, if anybody wants the slides, you can sign up at the link I have here on the screen. And I'm also, in the celebration of kind of the Zephyr Development Conference, I'm giving folks a pretty substantial discount on the NRF 9160, or NRF 9160 rather. So feel free to check it out. I've also written a bunch of articles on my website about Zephyr across many different subjects. So feel free to check it out, reach out. Love the chat.
Great. Thank you so much, Jared. That was great.
Thanks, everybody.
Yeah, thank you, Jared.
Thanks, David.